let's say I have some function f that is continuous on an interval between a and b. And I have these brackets here, so it also includes a and b in the interval. So let me graph this just so we get a sense of what I'm talking about. So that's my vertical axis. This is my horizontal axis. I'm going to label my horizontal axis t so that we can save x for later. I can still make this y right over there. And let me graph this right over here is the graph of y is equal to f of t. Now, our lower endpoint is a, so that's a right over there. Our upper boundary is b. Let me make that clear. And actually, just to show that we're including that endpoint, let me make them bold lines, filled in lines. So lower boundary A, upper boundary B. We're just saying, and I've drawn it this way, that f is continuous on that. Now, let's define some new function. That's the area under the curve between A and some point that's in our interval. Let me pick this right over here, x. So let's define some new function to capture the area under the curve between a and x. Well, how do we denote the area under the curve between two endpoints? Well, we just use our definite integral. That's our Riemann integral. It's really that right now, before we come up with the conclusion of this video, it really just represents the area under the curve between two endpoints. So this right over here, we can say is the definite integral from a to x, I should say, from a to x of f of t dt. Now this right over here is going to be a function of x, and let me make it clear, where x is in the interval between a and b. This thing right over here is going to be another function of x. This value is going to depend on what x we actually choose. So let's define this as a function of x. So I'm going to say that this is equal to uppercase f of x. So all fair and good. Uppercase f of x is a function. If you give me an x value that's in between a and b, it'll tell you the area under lowercase f of t between a and x. Now the cool part, the fundamental theorem of calculus. The fundamental theorem of calculus tells us, and let me write this down because this is a big deal. Fundamental theorem, that's not an abbreviation, theorem of calculus tells us that if we were to take the derivative of our capital F, so the derivative, let me make sure I have enough space here. So if I were to take the derivative of capital F with respect to x, which is the same thing as taking the derivative of this with respect to x, which is equal to the derivative of all of this business. Let me copy this. So copy and then paste, which is the same thing. I've defined capital F as this stuff. So if I'm taking the derivative of the left-hand side, that's the same thing as taking the derivative of the right-hand side. The fundamental theorem of calculus tells us that this is going to be equal to, f lowercase f of x. Now, why is this a big deal? Why does it get such an important title as the fundamental theorem of calculus? Well, it tells us that for any continuous function f, if I define a function that is the area under the curve between a and x right over here, that the derivative of that function is going to be f. So let me make it clear. Every continuous function, every continuous f has an antiderivative, derivative capital F of x. That by itself is a cool thing. But the other really cool thing, or I guess these are somewhat related, is remember, coming into this, all we did, we just viewed the definite integral as symbolizing as the area under the curve between 2 points. That's where that Riemann definition of integration comes from. But now we see a connection between that and derivatives. When you're taking the definite integral, one way of thinking, especially if you're taking a definite integral between a lower boundary and an x, one way to think about it is you're essentially taking an antiderivative. So we now see a connection connection. And this was why it is the fundamental theorem of calculus. It connects differential calculus and integral calculus. Connection between derivatives, and, or maybe I should say antiderivatives, derivatives, and integration, which before this video, we just viewed integration as area under curve. Now that we see it has a connection to derivatives.